So today we will discuss aeroacoustic models. Last time we have discussed about how to limit acoustic propagation, and now the question is, when we base our derivation on compressible flow equations, can we get out somehow a model which describes us how the sources look like for acoustics, and how can we compute then the wave propagation? So in this thing, we will discuss the starting of aeroacoustics, and the starting of aeroacoustics is clearly Sir James Lighthill. And Lighthill had the great idea to rearrange the compressible flow equations in such a sense that he gets out a wave equation. So he has on the left hand side the wave operator, and everything what doesn't fit to the wave operator he put to the right hand side. So it is an exact formulation, but we will see all the challenges we have. At this time, it was in 1952, 1954, where he did these very important publications. He still, at this time, it was not possible to solve this inhomogeneous wave equation numerically on the computer due to the restricted hardware resources. So he neglected somehow that there are any obstacles there, and used Green's function of free radiation. So as we have also discussed last time in acoustics, then you can transform the partial differential equation into an integral formulation. And then for simplified setups, you can even get an analytical solution, or at least approximative analytical solution. And then there was Curl, who realized the idea of Lighthill, and then transformed the equation in such a sense that you also can take into account obstacles within your computational domain, at least solid bodies. And the full general integral formulation then was Fox, William Hawkins, who even can take into account rotations as you have for helicopter noise and so on. Very interesting is then also a simplification of Lighthill's analogy, leading to vortex sound, because that gives even more physics in, because actually the voices are generating sound, and you can scale the comparison between vortex size and the radiated wavelengths of the waves, and these are more or less all called series. However, you can also look for the idea of perturbation ansatz. A perturbation ansatz is always an ansatz where you say, okay, I have some ambient quantity which are large, and then I have whole perturbation. Such and get out for the quantities, which are in our case then the acoustic quantities. It is clearly approximation, but a very powerful method used in all disciplines of physics. Yeah, and we will also then have a discussion and compare the different aeroacoustic analogies, and also not only the analogies but also the for cylinder and cross flow, and to look what is the outcome. Yeah, because with the perturbation equation we will be able to get out directly also within the flow domain acoustic quantities, at least for low Mach numbers. However, for all the analogies, you don't have really a separation between acoustic quantities. Let's take the pressure, acoustic pressure, and dynamic pressure. So you will always just get the overall perturbed pressure, which we will call with P prime. Okay, so let's go into the details. Hopefully afterwards you understand the so how sound is generated out of a flow, and that will be, let's say, our main topic we want to achieve here. Clearly, when you want to do a simulation to get flow-induced sound to noise, for example, for a fan, as is shown here, that is a very complicated task. So first of all, we have to ask ourselves what error can occur. Yeah, so that means for such a complex task, we should have a good knowledge what aeroacoustics effects can occur, and then look at a specific problem if this can occur at our specific problem, for example, the fan. So a very important thing here is always, can we model the flow as compressible or incompressible? We will see shortly. Okay, so when we know about the effects we have to take into account, we can choose a appropriate aeroacoustic model, the computation, and then very importantly always is visualization. We see how they just look like, how the radiated sound looks like, take monitoring points, compute the sound pressure level, but also really do visualization of isosurfaces, of the sources, of the waves, and so on. Okay, so let's directly start with the great idea of flight hill. In our first chapter about the basics of flow, we have introduced the so-called momentum tensor. And the momentum flux tensor has here the first part, which is density VIVJ. We call it also the Reynolds stress tensor. Then we have just between the pressure and the ambient pressure. And we have here our viscous tensor, taking into account any viscosity. Okay, so with this momentum flux tensor, we can write down the momentum conservation as shown. Now, in the first case, we assume we do not have any flow. So, no flow, which means this term cancels out because there is no flow. And the tensor cancels out, which means we will get a reduced momentum flux tensor. Therefore, we have the super zero, which is just a perturbed pressure, yeah, or pressure fluctuation at prime. And that we can also rewrite with the constant speed of sound by a perturbed, not a perturbed, sorry, a fluctuating density. Now, that means when we rewrite now our conservation momentum, since the momentum flux tensor reduced to the form, get here this equation. Now, let's also write down the equation we have here for the conservation of mass. Yeah, and now we know we do the same operations as we have done on deriving the linear wave equation. We try to get rid of these two, which means here we have a space, a time derivative. We will apply here a space derivative. So we will have here dx. We will, and then we which means that according to this operation, this term will cancel out, and we will have, as we see here now, the second time derivative minus the second space derivative. So we have here our classical wave operator. On operator, our fluctuating density is equal to 0. That is important, yeah? So that means if the initial conditions are 0, all boundary conditions are 0, we assume free radiation, so at infinity the fluctuation of the density will be 0. What you can get out is just 0. But that's clear, we don't have any. And please consider we done the derivation in the case of null flow. Okay, that is, I would say, sounds correctly. And now we will take the case of a flow. When we take the case of a flow and we take the differences of our momentum flux tensor, the total momentum flux, minus the flux tensor we obtain in the no flow case, then we end up in these parts here, and we will this Li, and this is then the so-called Light-Hill tensor. And for the Light-Hill stress tensor, as we see here, we have actually 3 terms. And these 3 terms I just will write here. So this are as follows. We call this here, I take it in red because that is very important. So this is the first here. Term is called, as already called before, ring. It's very difficult with the second part, which is this part here, we call the excess. So you see, this is just important if we have fluctuations in the pressure, fluctuations in the density, very important term at high Mach number, where also the temperature is of great importance. And we have the last term, and the last term will be. Okay, so in this sense, now we can rewrite the momentum equation as follows. So there is just a manipulation of the momentum equation, but we do not change anything here. As you see, that actually you could cancel out term here. Yeah? And then it's clear it's the classical momentum equation. We just have extended it with our momentum tensor pi 0, which will for the low flow case, but it would also cancel out. But in our case, we want to have it in. And then we rewrite it by this relation here. Here, we put in this reformulation of the conservation of momentum. Yeah, and we know the conservation of mass. Please also consider this additional term here actually is 0 because the time derivative of a constant is 0, so we can manipulate the conservation of mass in such a sense. And now we do the same as we have done before. We want to get rid of this term here. Yeah, which means we do a space derivative here, a time derivative here, and then we subtract. Doing this, we again get our inhomogeneous wave equation. We have our standard wave operator here, but now, very importantly, we have a right-hand side which is different, yeah, from zero. And since we had to do this, and we, as you can see here, the second space derivative on the light-hill tensor. So it is also the same as you take twice the divergence of this light-hill tensor, giving you at the end the scalar. But I think in this index notation, it's even easier to compute it. And this is a new equation. And what you have seen is that we have done no approximation. Yeah? So there is no approximation. We just have rearranged the equation of mass and the equation of momentum, and just did the following operations that we get out here an inhomogeneous wave equation on the left hand side. And well, which means knowing this source term, which is fully written, we can compute the radiated waves. Now let's have a closer look, and that will be our job on this inhomogeneous wave equation. But I think it's a great idea what has been done by Lighthill to first say, okay, I look at my compressible flow equations, what I have there. I know that they model the flow as acoustic waves. I look at the no-flow case, I look at the flow case, what is the difference? And the difference should be the sources. And I always try to get a reformulation for a wave equation. Okay, so this Lighthill stress tensor, as discussed before, has three terms. The first term is Reynolds stress term. We will see it's the main term for low Mach number and high Reynolds number flows. We have here, which is important just for high Mach numbers, where also the temperature plays an important role, and we have then somehow a complex constitutive relation between pressure and density. And we have a viscous term is mainly a term damping acoustic waves, but for all different cases of flows, high Reynolds, low Reynolds number, high Mach number, low Mach number, it is mainly a term which is related to damp acoustic waves. However, and that is the important thing, we have an exact of the fluid dynamic, and we have done no approximations. Important is clearly, as you see here, because we not only have to look at the wave operator. Wave operator is a linear operator, but the source term, well, the source term is a nonlinear term, as you nicely see here. So in a simple approach, which is clearly not fully grammatically, but you could somehow will the total velocity is somehow the velocity. If this is correct, we will discuss, but I do it in an additive way. You could also do it perhaps in a multiplicative way, but it includes, that is important, it includes both. It includes flow structures and wave structures. And then it is clear that this term here is a nonlinear term. So we have nonlinear acoustics, which could be due to shock waves. Since we have the interaction between flow structures and acoustic structure, convection of by the flow is taken into account, and also attenuation due to actions because your tensor there is taken into account. So we take everything into account correctly. We have done no approximation, so we have the full interaction of our waves with the flow structures. But clearly, we also now already see here, and that is important, yeah, this right-hand side is not a standard right-hand side of a partial differential equation because it not only includes sources, it also includes the unknown at the end, what we want to compute, because we want to get out actually, we want to get out actually the acoustic particle velocity, or we want to get out the acoustic pressure. Yeah? So it also includes this part here. So it also includes this part here. Yeah? And if we look, then this prime, and that will superposition P plus P, or however you do the decomposition of this overall pressure, the fluctuating pressure P prime. So the right-hand side is not only a source term, it is also an interaction term between flow and acoustics. So the main challenge is clearly we can compute the sound. That is, but we just can't compute the sound if the light hill tensor is on, and that we can compute, but we have to set of complex in the whole computational domain in order to be able to compute right hand side. That means we have to resolve all flow mechanisms and all acoustics mechanisms, all interactions when we solve the compressible fluid dynamics equation. Now this clearly sounds a little bit strange, because when we do this, why then doing again and solve for the now right hand side the acoustic wave equation? Consider an airplane. Yeah, for an airplane, the flow will be restricted. So you can have a restricted domain where you do this compressible flow computation and try to resolve all scales, all acoustic, all flow structure scales to be able to compute the light tensor. But we are interested what is the acoustic pressure at a difference of 5, 10, or even more kilometers, because we can hear the sound. So it still somehow makes sense. Yeah. But what we should also be aware of is that there is no separation in interaction and propagation. Yeah? That we already discussed. So the right-hand side is not a typical source term of a partial differential equation, because it includes also the unknown acoustic pressure we want to compute, or unknown acoustic density we want to compute. Okay, so it is a nice and great idea at least to have some insight in aeroacoustics, this light hills inhomogeneous wave equation, but on the one hand, it's not really practical because we need high resolved compressible flow computation, which in most cases is not feasible. Yeah, so you will have too much unknowns, you cannot compute it. On the other hand, we see even if we are able to compute it for some, let's say, academic setups, okay, we have no separation. Okay, do you have any questions? So, simple summarizing, the light hill idea was, in this sense, just a reformulation of the compressible flow equation. nothing more. We get a nice inhomogeneous wave equation, but we have to discuss what is this right-hand side. And we have seen the right-hand side is a term including the solution variable, which is in our case the fluctuating density itself. Yeah, so including the acoustic density, we are interested to have and compute the acoustic density, acoustic pressure, acoustic particle velocity directly. Do you have some questions concerning this first part? We will have further discussion about this equation. You have to switch. Okay, no questions. Okay. Okay, so let's go on and have further discussion. And this is, in this case, the practical application. Yeah. And we have a very nice practical application at low Mach number flows. Yeah, you know the Mach number is we know, let's say our medium is air, so we have 340 meters per second for the speed of sound. And so you see, even for the flow around the car, if you are driving even 200 kilometers per hour, you will have somehow a Mach number 0.1, 0.2. And you know somehow in flow dynamics, you have a limit concerning incompressible and compressible flow. And for most cases, this limit is about 0.3. So if the Mach number is smaller than 0.3, in a lot of cases, you can model the flow as incompressible. And that clearly then makes a sense. Okay. So let's assume we have low Mach number flow. So let's say Mach number about 0.1. Then we can find the following. Let's assume we have here a vortex structure, a eddy with size small, which will generate the acoustic wave with a wave number lambda, and the dimension of the region should be capital. And it was possible by the method of asymptotic to show that if the Mach is small and we have an incompressible flow that we can assume because the Mach number is so small, and we have this region divided by this about, and matching this compressible eddy core scaled by small l to the surrounding acoustic fields number lambda, then you find out that the leading of the light hill tensor is just this Reynolds stress tensor, but very importantly is this IC. So it's difficult sometimes. This thing. No. Okay. And you know, that makes sense because an incompressible flow means you do not model any wave structures because we know waves can propagate in a compressible medium. And then you really have a separation between flow and acoustics, which means that you do an incompressible flow computation, you compute the light hill tensor, which is now just a mean density, and the incompressible velocity. Now we have a real source term, and with this real source term we can solve our inhomogeneous wave equation, and we get out a perturbed density, or the relation to the pressure over the speed of sound, a perturbed pressure. And clearly in the far field, this prime quantity, fluctuating pressure, fluctuating density, will be the acoustic density. You will have no flow, so that just can't be acoustic density. And you call this a hybrid approach, which means you perform an incompressible flow simulation, you compute the sources as shown here out of your incompressible flow velocity, and you solve Lighthill's inhomogeneous wave equation. And what out again, the fluctuating density, as well as when you rewrite it for a fluctuating pressure, and this will converge out flow to the acoustic pressure. And that is now somehow senseful. As you can see, we have the restriction to small numbers, so that it's an incompressible flow. What is also possible is the following. You always know that doing a spatial derivative of numerical data reduces clearly the accuracy, and we have to do a second order space derivative. However, you can also rewrite the second order space derivative in the case that it is an incompressible flow, where we know that the divergence of this velocity is zero by this term. Yeah? So you see, you can reduce the second order derivative by first order derivatives of your computed incompressible flow velocity. And further on, and that has been done by Ribner in the 1980s, you can also express this term here, which is the source term of the Lighthill's inhomogeneous wave equation for an incompressible flow model by the Laplacian, as you can see, pressure. We have to neglect it. Yeah, but for such cases where you have low Mach number, high Reynolds number, the viscous term is so small that you fully can neglect it. So you take the momentum conservation and apply the divergence on it, and then you get directly that instead of taking the incompressible flow, you can take the computed incompressible pressure, and the Laplacian of it is equivalent to the standard source term of the Lighthill tensor for the incompressible case. This is also nice because you have to consider, instead of a vector, when you do the flow computation, you just have to store a scalar for all your finite elements or finite volumes, whatever method you are using to solve the incompressible flow equations. So this is a nice relation, and it is even more important because in fluid dynamics you have special algorithms how you solve the incompressible flow equations, and for this you sometimes do a splitting, and in this splitting you always have to solve for the Laplacian of the incompressible pressure. So you already know this Laplacian of the incompressible pressure, and so you don't have to do at the end, when you have computed your flow, do the second space derivative on this incompressible pressure. So really this term, the Laplacian, is within the solution algorithm for a lot within a lot of commercial and clearly also academic code. So this is then a very efficient way and clearly everything currently discussed is restricted that we have and we can model the flow as incompressible flow. And there was a further approach. This further approach was by How, and it is the vortex. And it also that you can rewrite this. Okay, I just see that there is a small mistake. No, it is correct. So that we can rewrite this term here now by these two terms. So this is just by vector identity that this term can be written by this term here and this term here. And this omega is vorticity. And we know, I should perhaps write it, the vorticity is computed by the curl of the flow velocity. And in our case, which is incompressible flow velocity. Okay, and then by looking at these two terms, you can derive, and that has mainly been done by How, that the second term is a small production term for acoustic waves. So you more or less can this term, and instead of our standard term in the inhomogeneous wave equation of Lighthill, you can have this as a source term. Yeah? Where you see it's the divergence of the cross product between vorticity, which is the curl of the velocity, and the incompressible velocity. And that is a very nice source term because here you can do a lot of analytical derivations and then really can show that for a single vortex, you even get for a simplified propagation domain an analytical solution for the inhomogeneous wave equation and then can directly see how a single vortex generates acoustic sound. But importantly, as we see, it is an approximation. Yeah? So all what we have discussed up to now are analogies, but they are all based on the Lighthill idea. Yeah? And we just have done simplifications. Yeah? But the full inhomogeneous wave equation of Lighthill, well, to solve it, we have this problem with the right-hand side term of the inhomogeneous wave equation, which is not a pure source, yeah, because it includes already interaction, nonlinearities between flow and acoustics. And just in this restricted part where we model the flow as an incompressible flow, we get rid of these interactions between flow and acoustics in the source term, and then we have a machinery perform an incompressible flow equation, compute the sources, which are now real sources by this Lighthill tensor, and then solve the inhomogeneous wave equation. Okay, do you have any questions here in up to now? So we have seen that the starting point of aeroacoustics was really in the 1950s by the idea of Lighthill, and then a lot of other researchers mainly focused at this time in Great Britain. They developed further simplifications or further physical insight, but the starting point was the idea of light hill. Okay, so what was actually the physical problem Light Hill was working on? And that was the jet noise. Yeah? At this time, they wanted to reduce the extreme noise generated by the jet you have due to the turbulent nozzle flow. And they wanted to reduce this noise generated by the airplanes. Now, Light Hill had this inhomogeneous wave equation, but as I told you, at this time it was not feasible to solve clearly this partial differential equation. So his idea was, well, I'm not so interested to really solve the equation. It is enough when I have some approximation and then get the scaling. So how does the acoustic sound power scales with the velocity of my flow? And that was the main investigation Light Hill did. And so he thought, well, perhaps it makes sense to transform the partial differential equation to an integral equation. And he clearly also knew at this time how you can do it. And he also knew at this time the far field approximation. And for him, it was clear, for me, it is important to rewrite then this for the far field, because I want to know what is the acoustic pressure at a big distance, and how does acoustic pressure or the acoustic power scales with the velocity exactly coming out here of the nozzle. And then to have an idea what to do and how you can reduce the generated noise. Okay, now you know, in order to come up from the partial differential equation to the integral equation, you need for your computational setup the exact Green's function, which is simple if we have free radiation, but here we do not have free radiation. Yeah? We have here the nozzle clearly can be perhaps modeled as sound hard, but it's an obstacle. And so Light Hill did the following. He was just neglecting the nozzle, and he investigated now the noise for. Okay, now for free radiation, we clearly know our Green's function. So what you get out now is the following, that this fluctuating is nothing else as the second spatial derivative, which is with respect to the observer coordinates. And you have to integrate this Light Hill tensor over the source term, yeah, where we have the source y. Okay, so in this sense, we have now an integral formulation, and we can now also apply far field approximation, which should give us at the end at least an approximate solution for P prime, and actually P prime will convert to the acoustic in the far field. where we are far away from the jet, where the flow velocity is equal to 0. Okay, and that we know, we have discussed. So we know that this retarded time, which is this argument we have here, yeah, we approximate as this. And we know that this amplitude decay can be approximated just by 1 over the absolute value of the observer coordinates. And we can rewrite a spatial derivative by a time derivative in the far field. So these are our main approximations we do, and we then substitute into our integral and get our far field approximation for P prime. Yeah, and now we have the following, that we have to integrate here over this term. We do a second time derivative, which is always easier as a second space derivative, and just have this scaling in front of the other terms here to get the acoustic, to get the pressure fluctuation, which converges to the acoustic pressure already in the far field. And this is now a very important equation, because with this equation we can do and look how does the acoustic pressure scales with the velocities, with the flow velocity, and we can even compute then the scaling to the acoustic power. And that we are doing here now. So we try to get a scaling of the acoustic power, as shown here. So we want to get a scaling of the acoustic power. And what we consider here is that we have a turbulence region here. And in this turbulence source region, we have individual vortices as shown here. And we want to see how much acoustic power is generated by such a vortex. Now, the characteristic frequency can be, or at least is proportional to the velocity over L. Yeah, and L, right, is here. L, as you see, is the diameter of a single vortex, and V is the velocity. V is the velocity of L is the diameter, and then you get out the frequency. You see, this will be the frequency also within the acoustic sum. Now we have the relation in acoustics between wavelengths and frequency. Yeah, and the scaling will be in such a sense that this should be, that should be one. That shows us that this diameter of a vortex divided by the Mach number is really large toward 1. And that allows us that we can assume that our acoustic sources are compact, so the wavelength is large. Let's write it. It's really to the diameter of a vortex. We can neglect any retarded time, and then the volume of such a vortex is L to the power of 3. Yeah, and that means our integral is simply the characteristic velocity of the vortex squared L to the power of 3, because we integrate over the volume, and mean density. So I just go back, and you see, we neglect here the retarded time, and this power is approximated to say, okay, here we take a velocity which is the characteristic velocity, so it is scaled. This is constant within the small volume of a vortex, and the volume of the vortex is the diameter times the power of 3. Okay, so this gives us now this estimation for the integral over such a vortex structure. Furthermore, the time derivative is proportional to the velocity over the diameter, so the characteristic length scale of a vortex that we already have used. I just remember that was this part. And so 1 over this term gives you the scales for a time derivative. We have a second time derivative, which means at the end, the acoustic pressure is proportional to this term here. So you see it is proportional to the characteristic velocity of such a vortex structure in the jet to the power of 4. And we have the standard scaling also with the distance. So it's 1 over distance. It scales with the standard distance law. And we can even make here the scaling is equal to our velocity characteristic over speed of sound. Yeah, and to get the acoustic power now, clearly we will assume a plane wave approximation. That would be the correct computation. We have to compute the closed surface integral of pressure multiplied by the particle velocity and integrate it over this closed surface. However, what we will put in here is that this is approximate. This is approximated by the acoustic pressure over mean and speed of sound. That is what we also have for a plane wave. So that means we have here the pressure squared, and assuming now that this is constant for such a small vortex, then we just put in this here, scale it with the surface, and what we get out is here the following, and that is important, that is proportional to the velocity to the power of 8. And this is the very famous 8 power called this sense here, mystic 8 power law of Lighthill, that he found out that for such a jet, the acoustic power scales with the velocity to the power of 8. And that led at this time that they changed the structure there of the jet engine and had the bypass, and with the bypass they could reduce the velocity, and since it is proportional to the power of 8, they were able to get a large reduction by the bypass, a large reduction in the velocity, and therefore a large reduction of the generated acoustic sound. You can also write this, since in the denominator we have here the speed of sound. We can also decrease the Mach number, so you also see that it's proportional to the velocity to the power of 3 and Mach number to the power of 5, which also tells you if you have very low Mach number flow, such a free jet, as we also call it, we have removed the nozzle, so you have just a region where you have a lot of vertical structures, so a typical jet there, and you consider free radiation. then it is clear for low Mach numbers, since this is scaled with the power of 5, you will have a very small radiation of the acoustic power. Okay, so you see that perhaps this, you have to look at some details. You will find it in the script. Perhaps it also sounds even a little bit easy, but at this time that was a real challenge and was a big achievement, which was done by Lighthill first. His idea to get up to this inhomogeneous wave equation, and then his idea to transform it to an integral formulation, assume free radiation, and get such an important scale law for even such practical application as the jet noise of airplanes. And that led to jet engines with a large bypass at this time, and you could reduce the generated noise by the airplanes tremendously, by this bypass where you reduced the velocity you had by the jet there. Okay, so what was clearly neglected again, which is not neglected in our partial differential equation. The partial differential equation is a general description. And that is important to realize. This simplification has just been done by transforming from the partial differential equation this idea or this description of aeroacoustics into an integral, because he used Green's function for free radiation. So as we had it, he just put the nozzle away and then he modeled a free jet radiating sound. And there was then the extension, and this extension first was done by Kerr, and therefore it is called Kerr's analogy. And he was also very skilled. By the way, Lighthill was a mathematician, but somehow also applied mathematician. So he did a lot of discussion with engineers, and the same is Kerr, especially perhaps if you have some information at Cambridge University in Great Britain. So they have a big mathematical department there, but it is a very applied department, meaning that they really do analysis of engineering problems. So Kerr then was also very good educated in mathematics, and especially for generalized functions. We will not discuss all the details, but I want to give you the idea of it. And the main idea is the Heaviside function. And I think you know the Heaviside function, at least in time. So where the argument is in time, so you can, by multiplying any signal with a Heaviside function, a simple Heaviside function, for example, in 1D time, and take here capital H. It is just as follows. It is 0. And for the argument being larger than 0, you have a jump, and it is 1. So if you multiply the Heaviside function with another function, you blend out actually here in this simple part, you blend out for all values of any function, the values for the time smaller than 0. But it's not necessary that your argument is time. It could be again a function. And that was the great idea by Kerr. So he introduced a space function. So f here is a function. And he defined this space function that if the argument is smaller than 0 within a solid body, if the argument is of this function is larger than 0, you are outside the body, which means you can blend out any obstacles. So he assumed solid bodies which cannot vibrate. So in this sense, but that are classical obstacles for us, which is, for example, the nozzle. He can blend out such structures by taking the Heaviside function of such a function f, which describes the surface of any body, of any obstacle within your computational domain. Yeah? So exactly you get the surface of when the function f is equal to 0. So this is really, as I have shown you here on the right-hand side, the simple argument is time. Here the argument is a space function itself describing the obstacles. Okay, so this is just written here. So just summarize this space function f, which is 0, larger than 0 or smaller than 0, according if you are inside the body, outside the body, or you're exactly on the surface of the body. And that means when you now multiply the partial differential equations with this Heaviside function, you blend out all these solid bodies, all these obstacles, for example, the nozzle in your computational domain, and you can again use then Green's function of free radiation in order to come up to the integral formulation, because the Heaviside function blends out the obstacles, and therefore it is like having free radiation. So how this is done? And I just want to show this for you for the mass conservation. Actually, what we have to do is we again have to manipulate the conservation with the Heaviside function, which means we just multiply them. Yeah. So as we have done for mass conservation, here just so. Okay, difficult to get black color because I want to close here. Okay, so you see we just multiply here with the Heaviside function. That's the first term. We have multiplied, that is the second term in the mass conservation, and just multiplied with the Heaviside function. So actually, this is clearly allowed. We don't really change the equation itself. But now we want to rewrite it in such a sense that the Heaviside function is within our time derivative and space derivative. It is not a problem to get the Heaviside function in derivative because it is not a function of time. So when you apply the product rule, we would again get here out of this term so this term would be just the Heaviside multiplied with the time of density. Yeah. If we do this for the space derivative, we have to be careful, yeah, because when you put in the function within the operator, you have to apply the product rule because the Heaviside function is also a function of space. Therefore, we have to subtract here this term. And so you see, not easy, what you get is a derivative of the Heaviside function with respect to space. But this is now allowed to be correct. We have done no approximation. It was just a trick to get this Heaviside function into the different operators. If you now do this, also for the conservation of momentum, and then do the same rearrangement as Lytle has done to come up to a wave equation, we get now it is extended because in addition to this term, we also have this term and we have this term here, just due to the fact that we have multiplied with the Heaviside function. But this is okay. And you just see we have here perhaps a problematic term because we always have a space derivative of the Heaviside function. Do you know what is the time derivative of the Heaviside function? When you use it as the argument of the Heaviside function is time. Have you ever seen this?
It's not differentiable.
Yeah, in a classical sense, but in the sense of generalized functions, you can do the differentiation. You have heard this in quantum theory or something?
Then it tends to infinity.
No. Yeah, that's correct. But which function it is, or which generalized function it is?
Dirac delta?
Yes, yes. Yeah, very good. Yeah, of course. Okay. And that is very nice because you know in the integral, our delta function plans out then the integral. Yeah? And you just have to evaluate the other term where the argument of the delta function is 0. Okay, and that is exactly what we will need. So now we can use Green's function for radiation. And this is this important relation. If you use function phi, and this is multiplied by the space derivative of the Heaviside function, then you can rewrite this volume integral by a integral. Now, this is a little bit different as a simple time integral. So you see actually what happens is that these additional terms, please notice, we have here the derivative with respect to space in this term here. So this will then be transformed from a volume integral to, as we can see here, a surface integral, exactly over the surfaces of our obstacles. On the other hand, for solid bodies, we know that we have no penetration into it, and therefore VINI is equal to 0. And at the end, what we get out is the following. Again, our standard term, which is the first order term here, which also goes with Lytle. But now we get the additional term, and in the general case, we also the viscous term, but here we just have to integrate the surface. And this is due to the that a smooth function phi, which is our source terms, multiplied with a space derivative of integrated over volume, just reduces to a surface integral of the smooth function. Yeah, it is also clear that the brackets here means it time. Okay, so this is now interesting in this sense because this perhaps reminds to the general integral formulation in acoustics. When you have obstacles, we also have to know the pressure, the acoustic pressure on the surfaces in order to compute the pressure at any observation point. So this is here very similar in the sense, and you find it in the script, that you can do this also with the approach we have discussed in the chapter acoustic. Okay, so in this sense, it means now we also have to know the light hill tensor in the volume where we have the flow, and for all the obstacles being there, we have to know the pressure perturbation, at least in, again, we'll neglect here the viscous curve. We need the pressure fluctuation on the surfaces. To be correct, you have to do a compressible flow. However, again, for low Mach numbers, perhaps you can do also an incompressible flow computation and then take here for this term the pressure fluctuation of the incompressible pressure. Now, you can again do the scaling just for this term here. And note that at far distances where the flow is equal to 0, we just get out the acoustic. We assume acoustically compact bodies, so the Mach number is very small. We can develop radiated surfaces which scales according to small l. The small l was for us the diameter of a vortical structure. And if you do this acoustic power, again, approximating here the acoustic particle velocity in the case of plane waves, mean density and speed of sound. And as we see, we divide the surface by individual small being equivalent to the vertical structure of an eddy. You just plug in there what you get out for the far field approximation of our integral. We have within this curves formulation. See at the end, and this thing is that the scaling here, I can write it with the power of 6. Here, scaling with the Mach number. Okay, and this is the 6th. So you see that this is even a better radiator for low Mach numbers because the Mach number just scales with the power of 3. In the other case, for this jet noise where we have no obstacles there, it was a scaling with the power of 5. Okay, so you see that this idea of curl leads to an integral formulation now which take into account obstacles. Clearly what you also need and have to extract from a flow simulation is the pressure fluctuation on the surfaces of any obstacles within your computational domain. Okay. Do you have any questions here?